So work is essentially the currency of life. If you want anything to happen, if you want to move something or you want to move yourself, then obviously this takes energy. And so we can work out how much energy by looking at the forces involved and looking at the distance or the displacement that we've moved. Now, when we did work done at GCSE, we said it was work done times force times distance done in the direction of the force. And it's the same thing here, except now we're going to look at the component of the force, which is acting in the same direction as the displacement. So what we end up with here is we end up with work done equals force times displacement times the cos of theta. But really this cos theta is attached to our force by here. All right, so showing the component of the force that's acting in the direction of our displacement. Remember back to GCSE, lots of different examples. The big one was obviously something going up a hill, and we talked about the fact that if you've got an object walking up a hill, could be a person, could be anything at all, then the force that has to be applied has to counteract the weight of the object. So if you want to move upwards, vertically upwards, and you're constantly applying a force upwards. So when we look at it, we looked at our displacement at the end, and we were looking at our vertical displacement, which is why we use the weight. So it's not a new idea, it's just a slightly different way of writing it, a slightly more mathematical way. And there's lots of examples of questions where you've just got to resolve this force into the horizontal, or you've got to resolve it into the vertical. Now, if you've got a graph, and you look at the area under your graph of a force displacement graph, well, obviously that's force times displacement, so the area equals the work done in joules. Now, dead straightforward if you've got your lovely geometric shapes that we know, like triangles and squares, and you know from past experience you can just split the graph up. But what do you do if you've got a curve? So you could have something in a situation where the force is constantly changing with displacements. Something that jumps to mind would be maybe, one doesn't jump to mind, but if you look at the force acting on an object throughout a journey, it might not be just straightforward, straight lines and what have you. So what you would do in this case is you'd still look at the area under the graph, and you've got a couple of options. You can either approximate that. You can say, well, look, that's more or less a triangle. There you go. And that's more or less another triangle. So I've got two triangles. Or you can break it up into little sections. You can break it up into lots of little trapezoids. Or you can just count squares as well. You can say, well, look, 1, 2, 3, 4, 5, 6, 7, and so on and so forth. And you know how much each square is worth because of the axes. If you do that, with these squares here, what's something easy and simple you can do is if you say any square that's over 50% full, you will count. Any square that's under 50% full, like this one by here, you don't count. And then overall, it should just average out. But it's the same thing. The area underneath these graphs equals the work done in both cases. Let's just shade that in so you know that that area equals that as well. Right then, some familiar equations here. We've got our kinetic energy equation, which we use all the time. And we've got our potential energy equation, which we also use pretty much all the time. I'm not going to do too much of these, just make sure you know the terms. Obviously, M is mass measured in kilograms, kg, V is velocity, has to be measured in meters per second. M is the same, G is the acceleration due to gravity or gravitational field strength, and that is in meters per second. And then delta H would be the change in height. I'm not going to do anything with those because we've used them a lot already, but this equation here, a little bit of a different one. You hopefully remember it from the forces section, but it is the energy stored in a spring. So you could have a spring which is stretched, or you can have a spring which is being compressed, so a string which is stretched, or one that's being compressed, and you know when you let go of it, it will return to its original shape. In other words, energy is going to be transferred, work is going to be done. So you do work at the spring, you stretch it, it's stores the energy as elastic potential energy, and then it releases it. So elastic potential energy. And K, remember, is the spring constant. And X would be the extension. So this equation comes from, if we look at this graph here, then we know that there's a relationship between the force and the extension, and there's a relationship, F equals Kx, where K, remember, is the spring constant. Now, if we look at the area under this graph, the area under this graph is actually the energy, okay? So if we were to look at the work done, so the work done would be equal to half F times X, because if we look at the triangle, sorry, the shape under the graph, it is a triangle, okay? So that's why it's a half F times X. And because F equals Kx, we can substitute that in, and that's where we get our F equals Kx squared from. All right, so it's a really quick derivation there. So well, let's put this over here so that makes a bit more sense. Okay, and sorry, I'm just going to rub this out because it looks quite messy, but you know that this comes from the area under the graph. Okay, now then, the whole reason we're looking at energy full stop and the other equations, which are quite straightforward, is so that we can do these kind of questions, right? Energy cannot be created nor destroyed. You've seen this in the course. It pops up all the time. It's a fundamental of physics and it affects everything. So here we've got the first example, ball, top of a hill, mass is 2 kilograms, and it's going to roll down the hill, which is 20 meters high. At the bottom of the hill, then we want to know how much energy, how fast it's going to go. So the reason this happens is because the potential energy at the top, so P at the top equals the K at the bottom. So we could put in mgh equals half mv squared. Now you could obviously just work out the potential energy up here and then say that equals kinetic energy and then do it like that, or do it in one go, because what we can do is we can see that certain things cancel out. So the mass, for example, cancels out. And we end up with V equals 2gh, all square rooted, and you would just pop that in your calculator. So what would it be? It'd be 2 times 20, 2 times 9.81 times 20, and then that will equal 2 times 9.81 times 20 equals oh, my calculator's gone a bit funny there, sorry. Do you know what? I'm going to let you work it out yourself because my calculator's just died. Oh, no, sorry, 19.8. So if we think about significant figures, I would actually write 20 meters per second because my answer can only be to 2 significant figures. Right then, now another example, just the same thing, is we've got a spring and the spring is compressed. It's compressed by 10 centimeters and it's going to launch this ball here up this ramp, and I want to know how high this ball will go. Now, there's a bit of information missing from this, okay, and that is the spring constant. So let's say the spring constant is, I don't know, 3.5. So say the spring constant of my spring is 3.5, and the units of the spring constants are newtons per meter. Now then, this question, if we look at it, it's going to be the elastic potential energy in the spring is going to be transferred into the kinetic energy of the ball, and then that's going to be transferred into gravitational potential energy of my ball. So In this case, because I know that it's a perfect world and all these questions we work in perfect environments, then I know that all this energy will be transferred into this energy and all this energy will be transferred into this energy. So in actual fact, I don't need to calculate this because it all just carries straight through. So in actual fact, all I really care about is that the elastic potential energy of the spring is equal to the gravitational potential energy of the ball. So in that instance, I can just use my equations to remember the elastic potential energy from the previous page was a half kx squared, or delta x squared I should say, and that is equal to mgh. So this time, less fortunate, my m's don't cancel out, so I'd have to rearrange it and put all the values in. So what I end up with is that h is going to be equal to k times delta x squared, all divided by mg, and I would just sub all my values in to find what that height would be. And my calculator's completely died now, so I'm not going to do this one. I'll let you work that out for yourselves. But just remember that because all the energy is transferred, then we don't have to work out the middleman here. We can just see what energy will go from here and end up into here. And we can see what height it goes to. Now we mentioned perfect world, and we don't live in a perfect world, and there is always going to be energy loss. So if you had a block moving at 20 meters per second, and this block is moving along a normal ground, and you stop applying a force to it, then it would stop moving. And the reason it would stop moving is because work is being done on the block due to friction. So if in this case I wanted to know what the frictional force was, I can use my idea of conservation of energy and work done to help me do this, because the kinetic energy lost by the block, because remember, it's going to go from 20 meters a second to here at the end having a speed of 0 meters per second, then the kinetic energy loss must be equal to the work done by friction on the block. So half mv squared is going to equal force times displacement. And hang on, we use s for displacement, sorry. I can write cos theta, but the force and the displacement are in the same direction as each other, so it's just going to be force times displacement because the cos is going to disappear, cos theta is going to disappear. And yeah, I've got all the values I need to make that calculation then. So let's just change that into FR so we know exactly what it is. So FR would equal mv squared over 2 times the displacement. And I just sub all my values in from here, and I would get my value of that. All right. There are a few other things we can do here. All right. So we can, instead of thinking about work done, we sometimes use power instead, because power, remember, is just the amount of energy per unit time. So it's the work done per unit time. So in some instances, we can think about power, and just like energy is conserved, power will also be conserved within a system. One other thing that it's worth noting here is there is another equation to this, because if power equals work done over time, then remember, power will also equal force times displacement over time. Displacement over time is velocity, so we actually have another equation. I'll write it in green here so we know it's a proper equation, and that is that the power of a system equals a force times the velocity, and that can be a handy equation to use sometimes, especially in these kinds of situations as well, where you've got a frictional force acting on it and you had some kind of original power. The other thing then to remember is that efficiency. So efficiency is the amount of work done here, and the useful work done is looking at how much of our work is useful, oftentimes by 100 to give us a percentage. Sometimes it can be just left as a decimal. But just remember, efficiency will work with work done, it will work with power, it'll work with any type of energy essentially, or derivative of energy like this.